So welcome to join our GCCM virtual meeting today. So I'm the host today. I'm a postdoc at Stanford University. For today's seminar, we have 45 minutes for the presentation and probably 10 minutes for the discussion and questions. So today we are pleased to have our speaker, Professor Valery Levitas. He is a distinguished professor and chair in engineering at Iowa State University, Departments of Aerospace and Mechanical Engineering. He earned his PhD and held leading research positions at the Institute for Superhard Materials of the Ukraine Academy of Sciences before working in Germany and the US. He introduced the rotational time armor cell to the US and pioneered in situ studies of mechanical and transformational properties. His work integrates multi-scale theory and experimental computational methods. So the title of his talk today is New Rules of Coupled Severe Plastic Deformations, Phase Transformations, and Microstructure Evolution under High Pressure. So Valery, please take over.
Thank you, Yao. So title is announced, and I would like to thank organizer for giving me this opportunity, and also my collaborators and funding agencies. So I will start with introducing concept of strain-induced versus pressure and stress-induced phase transformation under high pressure. Then we'll present our in situ experimental funding for several material systems. Then present new rules for strain-induced phase transformations and microstructure evolution. Also will include theory of starting four-scale theory, starting from atomistic to macroscale behavior of sample. And this macroscale theory is part of our coupled experimental computational approaches to extract material properties from heterogeneous fields in the sample and all tensorial fields. And then I will apply our approach to resolving puzzles of deep focus earthquake mechanism, and also show that even under hydrostatic conditions, microstructure evolution and plasticity play important role. Processes involving severe plastic deformation and phase transformation at high pressure are widespread in nature, engineering, modern technologies, and examples include high pressure mechanochemical and dynamic material synthesis, producing nanostructured materials by severe plastic deformation, surface processing, friction, military and geophysical and other applications. Each high pressure lab has a diamond anvil cell, two diamonds compressed sample within or without gasket. And what we are doing differently, we twist one anvil with respect to another, introducing large plastic shear, and this changes everything. So now it's rotational diamond anvil cell. It's similar to high pressure torsion produced with modified Bridgman anvils, which is routinely currently used to produce nanostructured materials. But there are two advantages here. So first, we can study everything in situ, and actually we resolved up to 600 points along diameter with X-ray beam. And second, much higher pressure can be achieved. So I brought this device from my former group in Kiev in 1999 to US, and this was beginning of study of plastic strain-induced phase transformations under high pressure. So currently we possess two our old RDACs and two dynamic new RDACs, one for slow motion, and we already use it, and another one for high strain rates will be tested for the first time at HPCAT in April. Key effect is that plastic strain significantly reduces phase transformation pressure. You see here our our in situ results, and in particular for phase transformation in boron nitride and in zirconium, reduction in transformation pressure is by factor of 10. The best example is graphite to diamond. On the hydrostatic pressure, it occurs at 70 GPa, if at all, and on the shear, it was recorded at 0.7 GPa. So it's 100 times reduction in transformation pressure. And if this could be scaled up, this could be a new strain-induced or defect-induced technology of diamond synthesis without temperature, catalyst, and practically without pressure. And it also has geological implications. So micro diamonds, which are found in Earth's crust in severely sheared zone, can be obtained directly by shear at the same place instead of subducting to high pressure temperature region and after appearance of diamond uplifting, what is assumed now. Well, also plastic shear leads to new phases, which cannot be or were not obtained under high pressure. And this is example of a new high density amorphous phase of silicon carbide, which was obtained at 30 GPa and large shear. Under hydrostatic condition, nothing happens at even at 135 GPa. And amorphization is a mechanism of damage of silicon carbide ceramics and other ceramics. And since this is reversible transition, the only way to study it is in situ study. Also, we recently revealed a new disordered superhigh phase of boronitride. You see it scratches diamond, and even cubic boronitride cannot scratch diamond. A problem is that modern thermodynamics, even if we introduce stress and strain tensor, cannot describe order of magnitude of pressure reduction. That is why we developed four-scale theory. And at atomistic scale, our goal is to derive lattice instability or phase transformation criteria on the action of all 6 components of stress tensor. It seems to be impossible due to large number of combinations, but actually we developed continuum phased field approach, and within this phased field approach we predicted analytically this criterion, so now we need just to check it. So under such loading, this is our criterion. Key point, it's linear in stresses. So in stress space, this is plane. And with this picture until plane is visible as a line, and you see dots here are molecular dynamics results, here DFT. So it's strong confirmation of this criterion, and we also determine 2 material constants. Then when we add 3 shear components, additional term appears, and but again, the difference between prediction and MD and DFT is within 5%. So, and this is for silicon 1 to silicon 2. So now we have simple analytical expression for transformation criterion on the general stress tensor with just 2 material parameters. And this is way beyond what was known before, mostly for 2 components and 1-2 papers for 3 components. We also approximated our results as 5th degree elastic energy, and you see here a good correspondence between elastic prediction and DFT for complex loading, for stress strain curves at large strains, even beyond the phase transformation, lattice instability and phase transformation. But real materials are defective, and that is why we need to take them into account. But first, I would like to mention that before appearance of this paper, high pressure community did not realize that there is fundamental difference between traditional pressure-induced phase transformation and plastic strain-induced phase transformation. Pressure-induced phase transformation started pre-existing defects, for example, different dislocation configurations, and which represent stress concentrators. So because number of defects is limited, one has to increase pressure to activate nucleation and defects with smaller stress concentrator. Here we introduce concept of plastic strain-induced phase transformation, which occur during plastic flow and started new defects permanently generated during plastic flow. So they represent defect-induced phase transformation and require completely different thermodynamic and kinetic description and experimental characterization. The only defect which can produce required strong stress concentrator is dislocation pileups. And we first developed simple analytical approach here, but then spent 10 years to develop a phase field approach to phase transformation, dislocation evolution, their interaction at large strain with various additional conditions. And now let's consider material which properties close to properties of silicon. So phase equilibrium pressure is 10 GPa. If you introduce single dislocation at hydrostatic conditions, phase transition occurs at 16 GPa. So then let's consider bicrystal under compression and shear. Dislocations nucleate at grain boundary and pile up against grain boundary, and then produce a strong stress concentrator for all components of stress tensor, which is proportional to number of dislocations. It can be 10, it can be even more. So we have huge non-hydrostatic stresses here, which satisfy our phase transformation criterion derived atomistically. So you see nucleation starts, and with further shearing, there is growth, coalescence up to steady state. And this happens at pressure average over the sample of 1.2 GPa. This is conceptual proof that dislocation pileup can reduce transformation pressure more than order of magnitude. But here we neglected dislocations in transforming grain. When we include them, you see that transformed region is smaller. That means plasticity plays a dual role. It promotes phase transformation by creating stress concentrators, but it also suppresses phase transformation by relaxing these stresses. And we found some combinations of shear stress and pressure for which solution without dislocations and with dislocations are approximately the same. So phase transition won competition over dislocations. And we summarized our nanoscale results as new possible routes for defect-induced material synthesis under high pressure. Now, we also obtained confirmation of nucleation and dislocation pileup with molecular dynamics and with concurrent atomistic continuum approaches. And with all three methods, dislocation pileup localizes at the grain boundary, producing super dislocation or step, and its length is much smaller than grain size even for nanograin materials. And this is opposite to what was generally accepted and used in this theory. And when we upgraded this theory by introducing this fact and grain size dependence of yield strengths, we found correlation between grain size dependence of yield strengths and minimum pressure for phase transition. For silicon 1, for silicon 2, we proved this. Namely, in the region of whole patch effect, when strength increases with reduction in grain size, theory predicts a reduction in transformation pressure. And indeed, for micrometer particles, transformation pressure is 2.5 GPa. For 100 nanometer particles, it's 0.3 GPa. In the region of inverse whole patch effect, when strength reduces, theory predict increase in transformation pressure, and indeed, for 30 nanometer particles, transformation pressure is 4.5 GPa. And this is a very strong confirmation of dislocation pileup mechanism. It is very unexpected because under hydrostatic condition, transformation pressure monotonously increases with reduction in grain size. Also, since we measure evolution of crystallite size in all 4 phases during loading, I placed here crystallite size at the beginning of phase transformation, and the same correlation can be formulated in terms of crystallite size instead of particle size. Now look at numbers. So in the hydrostatic pressure, transition pressure is 16 GPa. On the plastic straining, it's 0.3 GPa. So it's 54 times lower. And what is also important, it's the same under compression and at torsion. So it's independent of straining path. Well, TM Fox says that we never have seen dislocation pileup in nanograin materials, so it's not supported at all. Well, it's not surprising because in our simulation also after phase transformation and pressure release, dislocation pileup disappears. So it should be studied in situ. And here we just obtain very strong confirmation of this mechanism. At the very beginning of transformations, when we have just after nucleation, first nuclei appeared, you see that despite the 22% volume reduction, pressure in transformed three small particles is by 5-7 GPa higher than what we applied and what we have in parent silicon 1. So this is direct proof that there is strong stress concentrator and it can be obtained only with dislocation pileup. Okay, then we develop a completely different at the microscale, scale-free phased field approach. So here we take into account different crystallographical equivalent variants of high pressure phase and can consider a large sample with polycrystalline structure. And on the shear, you see that it's full of dislocations already. And despite stochastic grain orientation, most of them are already transformed. And you see here evolution, a very heterogeneous evolution in the selected grain, I mean of volume fraction of martensite and of high pressure phase. And we also determine parameters average over the sample, and you see how average pressure, shear stress, and volume fraction varies. And this is a theoretical basis to develop microscale kinetic equation, which I will discuss later. So for silicon, there are very many other interesting results. For example, for 30 nanometer particles, silicon 2 does not appear at all, but we obtain it under hydrostatic loading. We obtain it at 4.9 GPa at plastic straining. Silicon 3 during under hydrostatic loading does not appear for any particle size, but we obtain it at 0.3 GPa with small shear. Then nobody in static experiments could receive silicon 2 because it after pressure release, because it transforms to other phases. But you see, we obtain it in different combinations, even as a single phase. Also, nobody could obtain a reverse phase transition from silicon 1 to silicon 2 because it transforms to different phases. But because we obtain silicon 2 at low pressure, we could reverse this phase transition. So you see that we can manipulate synthetic paths to get to desired phases. Also, important problem is retaining single phase silicon 3 because of its unique properties. And one of technologies suggests quenching from 14 GPa and 900 kelvins over 3 days. And we quench from 11.6 GPa without temperature and within minutes, and we obtain silicon, single phase silicon 3 in quite large region. Also, observed very low phase transformation pressure warns that some phase transformation may occur in NEMS, MEMS during contact interaction and friction, and they should be avoided. Also, there is so-called ductile regime of machining of brittle ceramics, and here, to avoid damage, phase transformation is induced under pressure and shear as a mechanism of plastic deformation. But in all calculations in design, transformation pressure for silicon is 10 GPa, and we obtain it at 0.3 GPa. So there is significant room for improvement. Okay, next topic is strain-induced alpha to omega phase transformation in zirconium. But before this, I would like to mention that the main basic problem in studying plasticity, microstructure evolution, and phase transformation is that they depend on not only 5 components of plastic strain and pressure, which is bad enough, but also on the entire straining path, which leaves little hope to find some general laws. So what is straining path? For example, during compression, we have 3 components, plastic strain components: radial, axial, and shear. So we have three-dimensional line, which is straining path. And here we see two projections of this line into two planes. And for different points of sample, you see that there are completely different straining paths, completely different magnitude of final strain, and everything is very heterogeneous, which again, just sophisticated very much extracting information. But you know, saying transform evil to good because there are no other sources of good. So actually, because of we use this strong heterogeneity and complex loading passes, variety of loading passes, to get new rules for all these processes. So we study alpha to omega phase transformation in strongly predeformed zirconium. Strongly predeformed means that we produce multiple rolling until hardness, dislocation density, and crystallite size reach steady value and don't change anymore. This is crucial because we just exclude them as controlling parameters, which simplifies problem drastically. Without this, we could not get any rule. Everything is a complete mess. So this is our kinetic equation for strain-induced phase transformation, which we derived micromechanically, and it's very unusual. Time is not parameter. Instead of time, derivative is with respect to plastic strain, and ratio of yield strengths participate here. This is pressure plastic strain loading path. You see three examples here. This line is solution to this equation, and you see that all experimental points are very close to our prediction. So this confirms our equation, and we also determine all material parameters. Here you see evolution of volume fraction of high pressure phase and pressure for different loadings. Squares are minimum pressure for phase transformation, and you see that they are practically independent on radius. But we just discussed that along radius, straining path varies drastically. And for example, at symmetry axis, there are no shears, and shear increase with increasing radius. And this independence of radius means that minimum pressure for strain-induced phase transition is independent of plastic strain, its path. And this is first rule for phase transformation, and it has immediate consequence. The consequence that strain-induced phase transformations under compression in DAC and shear in RDAC don't fundamentally differ. That means if you prepare microstructure by preliminary plastic deformation, now everyone can study strain-induced phase transformation in traditional DAC. But of course, RDAC has advantages because it allows to independently control pressure and shear. And also it allows not only to start, but to complete phase transition at relatively low pressure. Well, friction between anvil and sample plays crucial role because it determines pressure gradient at maximum reachable pressure. And usual assumption is that friction reaches yield strength and shear, maximum possible friction, and this is used to obtain yield strength from equilibrium equation. But what we found that actually shear stress hardly reaches half of yield strength and shear. So this method has significant error. And that is why we developed DAC and RDAC with rough diamonds. So instead of standard asperities of 10 nanometers, we produce asperities of 300 nanometers by polishing and laser ablation. And in this case, indeed, we reach maximum possible pressure, possible friction, and we use this to determine pressure dependence of yield strength. So we slightly upgraded the equilibrium equation. We took into account heterogeneity along the thickness, and these two red terms appear. You see here experimental points for 5 different loading pressure distributions. And all of them are described by this simple expression for yield strength. But we know that at each point we have completely different plastic strain path, and also material acquires strain-induced anisotropy texture. But it's not here. We don't need this for description. That means that material behaves like perfectly plastic, which means independent of plastic strain and plastic strain path, and isotropic. This is first rule for plasticity. And problem is that this is everyone knows in plasticity that yield surface, this is yield surface in stress space, it evolves, so it depends on plastic strain path, and it acquires anisotropy. So how we can visualize our rule? To do this, we introduce new additional surface, which is fixed and isotropic. And during severe plastic loading, stress vector and actual yield surface touches our surface and then moves along it. And that means that material behaves like perfectly plastic and isotropic and independent of prehistory. Well, we connected this perfectly plastic behavior with steady microstructure. Indeed, you see at the beginning of compression, you see evolution and very heterogeneous distribution of crystallite size, and the same for dislocation density. But after a large plastic deformation, you see both of them are getting steady and independent of radius. And that means that dislocation density and grain size are steady and independent of plastic strain path, and pressure. And this is the first informative rule for microstructure. And then during phase transition, you see this is complete mess. But if you plot all these points versus volume fraction of high pressure phase, they both are along the same line. That means that during phase transformation, there is unique function of crystallite size and dislocation density for the crystallite size and dislocation density in terms of volume fraction of high pressure phase, which is independent of pressure, strain, and strain path. And also it's the same for smooth and rough diamonds. This is first rule for microstructure during phase transition, and it has important practical consequence. You see here, even at 14 GPa and corresponding large plastic deformations, we cannot reduce grain crystallite size below 60-40 nanometers. Here, in the pressure range of 0.7 to 3 GPa, crystallite size varies from 5 nanometers to 60. And so that means that phase transformation is much more effective way to produce nanostructured materials, especially nanostructured composites, than plastic straining alone. Okay, now we have 3 steady states. After rolling, this is dislocation density, crystallite size, and with rough diamonds, dislocation density is larger, crystallite size is smaller than with smooth diamond, which leads to reduction in transformation pressure by factor of 2, which is good. But bad point is, okay, we have 3 different steady numbers, and we claim that each of them is independent of plastic strain and strain path. But this is contradictory. If they are independent, it should be one number for all cases, but we have 3 numbers. And the same for yield surface. We have 3 different yield strengths. We have 3 different yield surfaces, but it should be one. So we arrive at new problem for which classes of straining material behaves along each steady state, and for which classes jumps from one to another. This is an unsolved problem. Without its solution, there is no general theory for phase transformation and for plasticity and microstructure evolution under severe plastic deformation. But if we will solve it, then we will be able to explain why different processing modes, for example, ball milling, high pressure torsion, equichannel angular pressing, produce different steady grain size and dislocation density. Okay, to develop science, it's not sufficient to talk about stress and strain tensor. We need to know them, but they are not measurable. So that is why we develop combined experimental computational approaches, in which, so we develop macro scale model with unknown material properties. We produce simulations, determine all fields, and feed them to what we can measure. And from this fitting, we determine unknown material properties, and also all tensorial fields. But there is also poor experimental problem. Well, pressure is usually determined by measuring with X-ray diffraction volume of crystal cell and using equation of state under hydrostatic conditions. But equation of state under hydrostatic and non-hydrostatic conditions differ significantly. And also with axial diffraction, axial strain does not contribute to X-ray pattern. That is why in our method, as experimental input, we use radial distribution of elastic radial and azimuthal hoop stress only without using equation of state. And after producing this long procedure, at the first step, actually it's an analytical step, we determine distribution of friction stresses. And you see that they indeed significantly lower the yield strength and shear. And we also formulated friction rules for alpha, omega phase, and mixture. I will not discuss this. This is our system of equations which we use for modeling. And if we don't do modeling at all and use just equation of state, then minimum pressure for alpha to omega phase transition is 1.36 GPa. But with our method, when we satisfy all our equations, it's 2 times larger. So that means the traditional method has significant error. Well, I believe this is our best result. We determine advanced kinetic for plastic strain-induced phase transformation. We already discussed this part, and we confirmed it, but it was only for points at the center of sample. Now we have points everywhere in the sample, in the entire sample, including resolving along the thickness. And so we introduce additional material, additional terms, additional material parameters, total 6 parameters. And after fitting, actually 2 of them, these 2, are unnecessary. And you have good correspondence between our lines, computation lines, and all experimental points. Maximum error is 0.7%, which for such complex phenomenon is 7%, which for such complex phenomena is unbelievable. And also from this kinetic, which can conclude that kinetic depends only on accumulated plastic strain and is independent on plastic strain tensor mode and its parts. We also have good validation for sample thickness profile and for elastic radial and hoop stress distributions. And after such strong validation, we are confident that our computational results reproduce correct fields. And in particular, this is plastic strain fields, shear in alpha, omega, and omega phase with further loading, radial, axial plastic strains. Key message here is that it's very heterogeneous and it produces very complex and heterogeneous straining paths. And actually, this complexity allows us to derive all tower rules, so that it's independent of parameters which we study are getting independent of plastic strain and plastic strain paths, because indeed we have a large variety of passes. And also we can model and determine evolution of volume fraction of high pressure phase, accumulated plastic strain, pressure, all stress components. So we have complete characterization of transformational and deformational behavior of sample, which we can use to analyze processes, to understand them, to extract our rules, and to optimize transformation deformation processes. Okay, next topic is new mechanical mechanism of deep focus earthquake. They occur at 350, 700 kilometers in such pressure and temperature range, and are generally assumed to be caused by shear bending due to phase transformation from metastable subducted olivine to spinel. But there are many puzzles, and two of them are: what are the mechanisms for jump from geological to seismic strain rates, which is 18 orders of magnitude? And also, how does metastable olivine, which does not transform for over a million years, suddenly transform within seconds? Well, we developed several new concepts, which allows us to address this and other puzzles. And main point is that we treat transformation in olivine like plastic strain induced instead of pressure and stress induced. And this was not done for any geological material before. And in particular, we have to use our kinetics, which is time independent. In our kinetics, rate of transformation is proportional to rate of deformation. You see, dt from both sides can be excluded. That means if we can provide large strain and large strain rates, we can provide large transformation rates. But how to provide large strain and strain rates? We found simple analytical solution for phase transformation in a shear band. And here we found transformation-induced plasticity, or TRIP, and this is simple equation for TRIP shear. So it's proportional to volumetric transformation strain, volume fraction, and such combinations of combination of shear stress over yield strength and shear. But in shear band, shear stress reaches yield strength and shear. We have 0 in denominator, and that means shear strain tends to infinity. And that is what explains huge shear strain and transformation shear bands in nature. Now, even more, phase transition causes large trip shear. Trip shear is traditional dislocational dislocational plasticity. So in turn, it causes phase transition. Again, trip shear, again, phase transition, and so on. So we have positive mechanochemical feedback and self-blown up phase transformation trip heating process. We describe this process with simple equations, and this allowed us to explain resolve quantitatively these two and several other puzzles. Quantitatively, I mean to within order of magnitude. This was poor theoretical paper. Now we have conceptual experimental proof. Well, olivine at room temperature, olivine does not transform to spinel under hydrostatic conditions at any pressure. But in RDAC, we transform it within 10 seconds, and in pressure range 15 to 21 GPa, which is relevant to earthquake. And we found first rule for this transformation, that transformation pressure linear reduces with increasing plastic strain, corresponding increasing dislocation density, and reducing crystallite size. We also found that after severe plastic deformation, crystallite size in olivine and spinel are getting steady and independent of plastic strain, plastic strain path and pressure. Then spinel is much weaker than olivine, so we expect strain localization. And indeed, our finite element simulation, this is quarter of sample, shows appearance of transformation deformation band. And that is exactly what we need for our theory of deep focus earthquake. So this is quite strong conceptual confirmation, but this is at room temperature only at the moment. Okay, and last point, I would like to show that for those who are focused on hydrostatic loading, that in this case also plasticity and microstructure evolution plays crucial role. So we studied strongly predeformed and annealed zirconium, and you see kinetics of these two are quite different of transformation. For predeformed phase transition starts earlier but ends later. Then crystallite size for strongly annealed, for annealed sample reduces significantly with pressure, then increases during phase transition and reduces again in omega phase. The same for predeformed, but to less extent. Then dislocation density for predeformed sample reaches 10 to 14, which is a respectable number even for severe plastic deformation technologies. But here just hydrostatic pressure. And then it reduces and increases again in omega phase. In alpha phase for annealed sample, we have order of magnitude reduction in dislocation density, and then again, it increases, reduces, and increases. Well, all our messy data, if we plot them versus volume fraction of omega phase, then we obtain the difference between annealed and predeformed sample is practically negligible. So this is first rule for microstructure evolution during phase transition under hydrostatic loading. So average domain size, microstrain, and dislocation density are functions of volume fraction of omega phase only, which is independent of plastic strain tensor prior to transformation and pressure. Now, during unloading, interesting, the domain size does not change. Dislocation density for pre-strain tensor does not change initially, but then reduces by factor of 2. And for annealed sample slightly reduces. And what is interesting, that final dislocation density for annealed sample is even higher than for strongly pre-strained tensor sample. That means that we don't need preliminary severe plastic deformation by multiple rolling. Just need to produce for annealed sample pressure loading unloading treatment, and we obtain higher dislocation density than after severe plastic deformation. This is very unexpected, and also change in dislocations mean plastic straining. So we observe it and the hydrostatic loading. That means there is no clean hydrostatic loading. There are huge internal stresses, even in poor phase, due to heterogeneity of polycrystalline materials. And measuring of microstructure is a way to characterize this and to upgrade plasticity theory, which neglects plasticity under hydrostatic loading. Also, microstructure affects strongly even equation of state for lattice parameters and for volume. So you see that key point is that initial microstructure and microstructure evolution affect phase transformation and changes during hydrostatic loading, and this should be characterized and taken into account because otherwise it goes to scatter, and this in particular explains significant scatters of behavior of zirconium studied in different labs. And to conclude, I introduced concept of plastic strain or defect-induced phase transformation during severe plastic straining and describe various important phenomena and new rules. Presented four-scale theory in simulation from atomistic to macro scale behavior of sample. Present coupled experimental computational results to method and results to extract material properties and all tensorial fields in the sample, address puzzles of deep focus earthquake mechanism, and finally demonstrated that even under hydrostatic loading, microstructure evolution and plasticity plays crucial role. Thank you for your attention.
Thank you, Valery. It's very nice talk, very informative. Now we're taking questions. Any questions from audience? Yes, Agir, please go ahead.
Can you exclude some increasing of temperature during the rotation of your imposed to one of the two anvils?
Well, even at there are data, preliminary data. Well, we do this at the moment at low strain, at low rotation rate. And due to thermal conductivity of diamond, there is no any increase in temperature. Even what was measured, it's not our work, but people who do high pressure torsion with ceramic or metallic anvils for large samples is, well, diameter is 1 centimeter, contrast to our 0.5 millimeter. So even in this case, and increase in temperature is like 10 degrees, maybe 20 degrees. So in our case, it's completely negligible. It's small even at 100 rotation per minute. And what will be at higher rotation rates, we plan to go to 4,000 rotation per minute. I don't know, but it will not be drastic. It will not be drastic. It will be maybe within tens of degrees. And this is if you will be able to extract information at high rotation rates, so at strain rates 10 to 3, 10 to 4 over second. This would be unique testing method because temperature is fixed. Usually temperature grows together with straining, with pressure. Here temperature is fixed. So this will be unique method, I hope.
Thank you.
Thank you.
Please go ahead.
Okay, how does this compare to shock-induced amorphization? Well, how to shock-induced amorphization? It depends. If this is plastic strain-induced amorphization, its mechanism should be very close, but there is additional effect of strain rate, which we plan to study. Not, of course, up to strain rates in shock, but up to 10 to 3 to 4. At the moment, we don't have this information, but so if you want to cause phase transition, you need to either pressure should be very high, or if pressure is low, then plastic strain should be significant. For example, in shear bend. Then if it's pressure-induced amorphization, it's completely different story. If it's relatively low pressure and large plastic shear in a shear bend, then I believe this is the same. And there are a lot of recent reviews, in particular, well, from Lawrence Livermore and Mark Myers. I'm sorry, what is this? Okay, there is there are various review now on amorphization in shear bends in various materials, metals, ceramics, and mechanism is very close. And actually, Mark Myers uses generalization of well, some advancement of our theory for interpretation of results of amorphization in shear bends, in dynamic shear bends.
Okay, Robert, I saw you raise your hand. You have a question?
Yes, thank you. Very fascinating talk. I think some of your slides showed a dislocation density of 10 to the 14. In my understanding, I'm a geologist, in my understanding, that high a density would render the substance almost amorphous.
No, because even, okay, in high pressure torsion to produce nanograined materials in metals, dislocation density, let me see. You see dislocation density 10 to 14 and it's order of magnitude higher. So even 10 to 15 does not cause amorphization. This is for metals. For metals. For geological materials, it depends. For example, we produce severe plastic deformation for olivine, and we did not observe amorphization. We
Okay.
did not. And honestly, well, and even for silicon, where I expected amorphization, but we produced slow experiments and we did not observe amorphization. I assume that if we increase strain rate, or when we increase strain rate, we will observe amorphization. So at the moment, classical mechanism of plasticity, I mean at such strain rates which we use, they are sufficient to accommodate prescribed plastic strain. But if it will be higher strain rate, then it's very probable that amorphization will occur, in particular in geological materials and in silicon.
And so as a follow-up, I'm wondering now if the dislocation density is still very high, as it will want to recrystallize, and it maybe by Ostwald ripening, it would lower its internal energy by producing a new product phase out of equilibrium with its hydrostatic pressure field. I'm wondering if stages, I know in geologic materials, amorphous silica can produce metastable phases in between that and quartz, just by lowering the internal energy, but not lowering it to the minimum. Is that possible in some of these experiments?
Generally, yes, because we are working at room temperature. You know, again, there is a large community which produces high pressure torsion for living. It's without in situ experiments mostly, but to produce nanograin materials, high dislocation density materials, and these materials at room temperature can stay for several years without changing grain size. So that means that maybe there are some exceptions. Maybe there are some exceptions. I am sure that what you said at high temperature will happen. Because yes, then we have dynamic recrystallization and yeah. So answer at room temperature, we did not see this. We did not see this. Again, from geological materials, we studied only olivine. Maybe other materials will produce some effects. But you know what you said, these metastable non-equilibrium phases which don't correspond to minimum energy, we produce them under shear. So we produce silicon, for example, silicon 2 at 0.3 GPa and phase equilibrium pressure. I am not talking phase transformation pressure under hydrostatic loading is 16. Phase equilibrium pressure is around 10, 12 GPa. And we produce at 0.3. Of course, we produce strongly metastable phases and because of you know, let's put in a such way. Locally, everything is according to thermodynamics, but under stress tensor. So that means that I showed you, we applied 1 GPa, but locally in transformed phase, we have 7 GPa. Why? Because there is strong stress concentrator due to dislocation pileups. So that means that we follow dislocation rules, but we follow thermodynamics rule, but on the stress tensor and strain tensor, and in the presence of defects and strong stress concentrator due to defects.
Thank you.
There was one more question, I believe, in chat. Let me see what we have in chat. Okay, probably it's not new. Okay, no, there were not new questions in the chat. So any other questions?
Any questions? Yeah, I think there's questions in chat, but I think the person who asked the question left the meeting. You want to briefly answer it? Or so the question is, does the temperature play an important role in shock-induced amorphization, or only high strain rate is responsible for this?
Okay. Well, temperature changes thermodynamic conditions and it accelerates process. So generally it should affect, but how it affects, I don't know at the moment in shock-induced amorphization. Well, for example, we just published paper on molecular dynamic simulation of appearance of amorphization, shear amorphization band in silicon 1 under simple shear. And in our case, the same result was at 0 Kelvin and at room temperature and at elevated temperature. So in our case, it did not matter. Also, in our case, even strain rate did not matter. Because what happens that this was ideal single crystal, and lattice loses its stability. So shear stress reaches instability limit. And then material just goes where it can go. And because, and actually it goes to melt at room temperature. Shear stresses drop to 0. Then from melt, it goes to amorphous solid. So shear stress, shear resistance reinstated. And then within this amorphous band, there is a cyclic transformation between amorphous, silicon 1, and silicon 4. So very complex picture, and it appears that it's independent on temperature and even, well, at least initial amorphization is independent of strain rate. So, but this is just one example, and this is MD. I believe that for various material system, answers will be different.
Okay, thank you. I think this is almost at the time.
Okay,
So
here is
yeah.
paper that looks into a bit from preliminary research. Some paper. Okay, thank you.
There's one more question you want to answer, like in the chat, from Fei Zhang. How to evaluate the effect of pressure gradient during the phase transition under high pressure?
Pressure gradient, we don't have, how to say this? In our case, we have various cases with strong pressure gradient on our scale. So we have, for example, pressure varies by 10 GPa along the diameter. This is not very large pressure gradient, actually. We determine everything locally because we measure everything locally, and we feed all our heterogeneous results with this local description. So I cannot see that pressure gradient in our pressure gradient range affect phase transformation. Now we have also paper when we fit it in simulation, non-experimental result with pressure up to 400 GPa. There is here, of course, a huge pressure gradient. And I hope that we could not do this. And then I will need to develop a non-local theory of plasticity. So it will be fun for me. But actually, surprisingly, everything was described properly with local theory. So, but this was just plasticity, no phase transformation. So at the moment, I don't see reason for our cases, which we studied, to take into account pressure gradient as governing parameter for phase transformation. Maybe in shock loading, this is more important, but in our case, it's not. And yeah, and then one more question I see appeared, that how to distinguish amorphous phase from melt. Well, by definition, melt does not have shear resistance. So what we obtain that shear stress drops to 0. For us, this is melt. I call this virtual melt. We have dozens of paper on virtual melting. That means that material, and this is at room temperature, so it's 1000 degrees of below melting temperature. Material melts. This is in silicon, this is in copper, in aluminum, 1000 degrees below melting temperature. And so distinguish differences. First, shear stresses. Amorphous phase supports finite shear stresses. Melt does not. This is one. Then temperature dependence of self-diffusion coefficient. So, for example, in our PNAS paper with Ramon Ravella, he studied, he showed that actually in disordered phase, temperature dependence is the same as in traditional melt. And also there is way to distinguish based on kinetic of recrystallization, because recrystallization because melting temperature and amorphization temperature differ, then recrystallization is governed by different rules. So this also can be distinguished.
Okay, I think we run out of time. In a few days, so you will see the recordings in our YouTube channel. I just shared the link in the chat window. Also, we will have GCCM conference from June 22nd to 27th in Washington, D.C. So we are currently calling for abstract. And also, we opened the early registration. So we encourage you to register and you can take advantage of discount rates. So before the conference, we probably have a few, virtual seminars on Zoom. So we're always looking for speakers. So if you have someone to nominate, please contact me or Dr. Tracy Vogler, who is the chair of the organizing committee. So thank you for joining the seminar today, and thank you, our speaker.
Thank you. Thank you to
Yeah, very
everyone.
nice talk. Yeah. Okay. Thank you, everyone. Hope to see you next time.
Bye.
Bye.